Hello, hello, hello. Welcome back. Today, long time no see. I saw you guys yesterday. Today is Sunday, 31st of May, and today we're going to be going through the physics paper 2 multiple choice. Apologies for the slight delay. I underestimated. That's not a word. I I completely underestimated how long it was going to take to like download all the papers, and I was like, guys, come on. Hope you, there was sports ball yesterday. Apparently that happened. So congratulations to the team for doing stuff. But I think today is really just going to be a case of getting through these multiple choice. I've got the 2024 papers for Edexcel, AQA, and OCR. And my plan is just to blitz through as much of it as possible. The multiple choice questions from them, mark them up, because with a lot of the mark schemes, obviously you just get answers and not like work solutions. And plus it's a good way to do sort of rapid fire cross syllabus paper 2 revision rather than sitting there because no one wants to sit there and watch me write sentences. Like not as fun. And there could be some interesting like strategies. So I'm going to put you guys over there. If I don't know a question, I'll skip it. But realistically for an A-level, I'm going to try and run it through. All right, let me quickly get to the multiple choice section. Oh, and as always, if there's like a particular paper that you want me to go through or a particular question from a particular paper, feel free to drop it in chat and I'll make sure to get to it. Now, let's do, we'll just do window. That's all good? Good, we can flick through, perfect, okay. So I'm not going to do this to time because I'm not quite sure even how that would work. I'm just going to go through 2024. Well, great, because that's what I'm doing. Okay. Well, also, full disclosure, I slept just badly last night. I don't know why, but I was up at like 5 a.m. and couldn't get back to sleep. I was like, come on, please, please. So if I'm not on top form, we will blame that. But let's see how well I do. All right, let's get into it. In which process is work done by an ideal gas? It is what it is. But also, like, it's still instructive, right? Because like you might have a bomb night's sleep right before your real thing, so you still got to sit there and do it. So why should I be exempted from that? Like, yeah. Okay, so work done. Nope, that's not what I meant to do. I meant to do this. So we know work done is pressure times change in volume. Doubling the pressure at constant volume, no, because nothing moves. Doubling the volume at constant pressure is work done by an ideal gas. Would that be work done by the gas? I'm still going to go for it. Technically, that would be work done. No, that'd be work done by the gas. Okay, cool. Because it's pushing the thing out. 3 molecules have this speed. What's the RMF speed of the value? So that's the root mean squared. So it's the 16V and 25. So these are the squares. That's the mean square, and you square root it, and that's the root mean square. So 20, that's 45 over 3 is root 15V squared, which is V times root 15, and root 15 is 3.87. So I'm going to go with that. Now, obviously, in the real thing, you would like fill in the bubble, but hey, I can do what I want. So ideal gas enclosed in an insulated container with a small electric heater. Initial temperature is that. The product of the pressure and volume is that many joules. Well, ideal gas, PV equals nRT. The gas expands at constant pressure. Does that much work? Oh, interesting. Interesting way of phrasing that. Product of pressure and volume is 5,000. Expands at constant pressure. So 5,000. What's the final temperature? So I think what we're saying is 5,000 is equal to thingy times 300. And the gas does this much work. I think that means it loses energy. Yeah, but the gas expands at constant pressure. Interesting. My brain doesn't like this. All right, I'm going to skip and come back to this one because that's how I would do the real thing. 11, air-filled parallel plate capacitor and resistor are connected in series across the terminals of a battery. I'm going to draw that out. So parallel plate capacitor and resistor. The plates of the capacitor then moved further apart. So C is equal to epsilon naught A over D. So if they're moved further apart, that means that C decreases. Now, V is going to be constant. So Q equals CV. A decrease in the potential difference. That's not going to happen because that's designated by the cell. A decrease in the charge held. I think that does happen, but let me check the others. Increase in energy stored, that's a half CV squared. So no, C goes down, definitely not that. Increase in capacitance, no, that goes down. Right, so that's correct. 12, which change will increase the efficiency of a transformer? Increasing the thickness, no. That's bad, that increases your eddy currents. Decreasing the frequency, I'll come back to that. I don't think the diameter of the copper wire in the primary coil has anything to do with it. Because that would in theory decrease the resistance of the wire, but I still don't think that's it. Increasing the distance between the primary coil and the secondary coil, no. Decreasing the frequency of the AC input voltage. Interesting. Okay. This was challenging. I'll come back to it now. Let me get the low-hanging fruit first. Because again, that's what I really want to demonstrate today. Prioritize. Signal generator supply. And also don't feel ashamed about like skipping and coming back to things. Like it's what you do. Signal generator supply, sinusoidal root mean squared of 7. Displayed in an oscilloscope. 8 vertical divisions. So if the root mean square voltage is 7, that means the peak voltage is going to be that 7 root 2, which would be 9.9 volts. And that would go up and down. So the total peak to trough distance would be basically 20 volts from top to bottom. And the screen has 8 vertical divisions. So 20 divided by 8 means there's 2.5 volts per division, which is C. Okay. 2 signals that have the same frequency are displayed simultaneously. Time base set to 5 milliseconds per division. Which row shows the frequency of both signals? Well, frequency is 1 over time period. And the time period, well, we can see that's 1, 2, 3, 4. What? 1, 2, 3, 4, 5, 6, 7, 8 divisions. So 8 times that, so that's 40 milliseconds time period. So the frequency is 1 over 40 times 10 to the minus 3 is 25 hertz. Okay. So then the phase difference is how far, what's the, so okay, so the difference is 0.6 of a large square. So if the time period is basically 8 divisions, and the separation is 0.6 divisions, what percentage of the thing is that? Well, that's 0.6 over 8, and it's going to be that amount of 2 pi's. So it's that 0.6 over 8 is the fraction of the 2 pi, which is through 3 over 20, so it's 0.15 pi, which is B. Nope, which is not B. I crossed out B, which is D. Guys, it is actually so much easier than you think to like accidentally pick the wrong, do all the right working and still pick the wrong answer. Bad. Transmission cable, many strands of wire. We have a frequency. What change gives the largest increase in the efficiency of the transfer along the cable? Well, we know that power loss is equal to I squared R. So doubling the current is bad. Doubling the voltage is good because that decreases the current. So that would make it go down by a factor of 4. Having the resistivity would have the resistance, which makes it goes down by a factor of 2, this loss. So that's not as much. Having the number of wires in the cable, well, no. So I'm going to go with A. Because to explain that one, having the number of wires in the cable, that will decrease the total area that the current moves through, which increases the total resistance and would actually lead to a decrease in efficiency. Electron enters a uniform magnetic field at right angles to the field. Non-relativistic. Weight per voltage. Are they directly proportional? Well, they are directly proportional. This is it's trippy when it comes to transmission cables, because the point is that they won't. The intent is not to lose the voltage in the transmission cable. So trust me, the way around this, that equation isn't going to work for transmission cables. P equals I squared R is the equation for heat loss in a transmission cable, because that's the whole point of step up and step down transformers. You want to step up the voltage when you're going from the generator to the wires, specifically because that decreases the current and therefore decreases the power loss. So that's the reason why we have transformers in the first place. I get what you mean about that, but remember, let's think about this, right? When we say doubling the transmission voltage in the cable, that is not, when we say we double it from 1000 volts to 2000 volts, we don't suddenly mean that 2000 volts are lost in the cable. And that is what you mean when you say power is V squared over R. That V in the V squared over R has to be the voltage lost in the cable, not the voltage carried by the cable. So it's a really common misconception and thank you guys for bringing that up in chat. That's why, like, belt and brace, like, the safe way to approach power loss in cables is always to go by I squared R. Okay. So an electron enters the uniform magnetic field. And also, thanks for I'm keeping an eye on the chat. So definitely leave any comments like that if you want me to clarify what I'm doing. So here, electron enters the field. So we know that the BQV, which is the force on the electron, equals mv squared over R. Okay, so what's the number of circuits completed in 1 second? So that's the frequency. We're looking for time period of circular motion. Cancel. We know R equals mv over BQ. Or rather, let's say we know that V is equal to BQR over M, but we also know the speed will be 2 pi R over T. The R's will cancel. The time period, no. Let's divide by 2 pi, because then we'll get BQ all over 2 pi M will equal 1 over T, which is the frequency. And Q is E, and so that's going to be D if this is an electron. Okay, that was fun. The following reaction occurs. That's the weirdest plus I ever seen in my life. All right. This is going to take time. All right, no, it's going to be fine. Going to be fine. So we consider the mass change. So that is going to be the 13.00007, not miscounting the zeros, and the 1.00728. So that means there's 14.00735 on this side, 13.99925 on this side. The mass defect is therefore 8.1 times 10 to the minus 3 U's. And we multiply that by 931.5 to get 7.5 mega electron volts, which is C. And again, we're really getting confused on our little plus signs, aren't we, exam? Okay, so we bombard it with neutron, nonsense happens, which statement is not true? This is not true. Wait, of the 3 nuclei, no, the 87 will be the biggest. So that's not true. I'll confirm that because I'm not just going to go with my first instinct when there's multiple choice, but still, this mass is greater than those masses. No, that is true because that mass does go down and gets released as energy. The binding energy of the neutrons is 0. That is true because they are already separated nucleons. Yes, the binding energy is bigger, even though the binding energy per nucleon is less because there are just more nucleons. So that's good. And I think I should do that as well. I should also, in cases like that, I'm going to clarify why it's not the others, just to fully explain it. Okay, so this amount of heat energy is released when this is burned. So we can get a kind of specific energy from that. Oh, interesting. Isn't that because they're all higher than iron? The reason, okay, they're all higher than iron. That's why fission happens. But if you track the binding energy per nucleon curve, it is definitely true that the closer you are to iron 56, the bigger your binding energy per nucleon. So I would expect this one, the bromine, to have the highest binding energy per nucleon. So if you're talking about why D is not true, binding energy always increases, even though binding energy per nucleon decreases, just because in each case you're multiplying by the mass number. So hopefully that helps. So here, sorry, I was referring to why A was true. A is true because they're all higher than iron. So it's just the binding energy per nucleon curve. It's because the bromine is going to be closer than the lanthanum will, and so the bromine will have a higher binding energy per nucleon. So this one will not have the highest. It will be the bromine. So here, the amount of energy released when 1 kilogram is burned. What is the mass loss? Well, let's go for E equals mc squared. But that's... This might be a trick question. It might be 0 because... Oh, wait, no. Maybe it is 0. Hold on a minute. Okay, this might be a trick question because it might be 0 because that's released from chemical reactions, not nuclear reactions. I don't think that release of energy... So it's to do with the chemical bonds, which is to do with electrons. So this might be a trick question. It might be 0, but if it's not a trick question, then this many 5.6 kilowatt hours, that would be 5,600 watts, which is a joule per second. So times 60 seconds in a minute times 60 minutes in an hour would be 2.016 times 10 to the 7 joules. And then we divide that by the speed of light squared, and we would get 2.2 times 10 to the minus 10. But that's only if we're converting the mass energy into the thermal energy and not the chemical energy. I'm going to go with, you say conservation mass. I'm going to go with 0 just because I think it's not coming from mass energy. It's coming from chemical energy being converted from the chemical bonds. But yeah, that I can see why that would trip people up. I'm not 100% certain on what they're going for there. Yeah. So here, nuclear radius is given by that. What's the nuclear radius of an element? Okay, so the thing here is okay. I can't remember off the top of my head, but I do know. Well, it also doesn't help that I don't have my formula book, which I really should have. Let's see if I can find. AQA math formula book, because I should be showing you. That's math. Yeah, here we go. Oh, that's math. Why do I keep getting this wrong? No, just a whole bunch of math formula books in here. Because I want to. Okay, let me see if I can find this real quick. So I should also show you how to use this, because what I'm going for here is. Okay, fine. I'll derive it first. So what we know is that the nuclear density is constant, right? So we know that the density between the two is the same. Density is mass over volume. And the mass is equal to the number of nucleons times U times over the 4/3 pi r cubed. So what we know is that r cubed is proportional to the number of nucleons, right? In other words, it's proportional to the cube root of the number of nucleons. And so what this means is that R1 over N1 to the third equals R2 over N2 to the third, which means that R2 is equal to R1 into N2 over N1 all to the third. In other words, if X is R, that would be R, and then X would be on the bottom, so it would be Y over X to the third. That's what I'm thinking, right? So that's how I get to D. Kilowatt hours. So yes, but if you remember, that's kilowatt hour. A watt is joules per second. So you can convert that into. That's why you multiply it by 3600, because that's how many seconds there are in 1 hour. So that is you multiplying by the hour for that unit conversion. Just going back to answer a comment question there. Right, now I do want to get the formula book, because I want to make sure I've got. There you go, physics. I want to make sure I point out where possible that you can use formulas in the formula sheet. Okay, so opening that up now. Cool. And I'll probably use this for all of them, because the equations are the equations at a certain point. But I want to show you where I could have looked that up, because here it is in the nuclear physics. Yeah, so I could have, instead of deriving it, I could have gone straight here. So could have made good use of that. Right, back to the task at hand. Let me just save so I don't lose anything. And I can keep going right to 2, by the way, when I have my next session. So, thank you. We get some orbits. Okay. Planet has a mass twice the mass of the Earth. A day on the planet is a quarter of an Earth day. What is the radius of a synchronous orbit? Well, we know that a gmm over r squared equals mv squared over r. Cancels. cancels, cancels. GM over V squared. No, but they didn't want it that form. They didn't want MV squared over R. Let me show you what other forms exist. Do they show you, or do you have to derive them? Gravitational fields. I'm looking for circular motion here. Where are my circular motion? Ah, here we go. Okay, so they don't give you one involving time period, but they do give you m omega squared r. So let's go for that one. You have to do a little bit of conversion here. So we know that for a circle, f equals m omega squared r, and we know that that is 2 pi over t squared r. So it's 4 pi squared mr over t squared, and that will be gmm over r squared. The m's will cancel. T squared, nope. We want r to be the subject. So gm over 4 pi squared. Oh, I could have, of course, gone straight to Kepler's third. What am I doing, guys? All right, so t squared equals r cubed. So what do we know? We know that m is twice as big. So in other words, we know that r cubed is equal to gmt squared all over 4 pi squared. And we know that the other r cubed is equal to g. This mass is twice the mass. A day on the planet is 1/4 of an Earth day. So it will become a quarter t squared all over 4 pi squared. I like to divide mine through because a lot of stuff cancels. And when you do that, the g's will cancel, the m's will cancel, the t squareds will cancel. In fact, let me do the other way around. So I'll do r cubed over big R cubed. We'll get this 1 over 16 times 2 is an eighth on the top after the gm and pi squareds cancel. And the 4 pi squareds will cancel as well. So in other words, r cubed is r cubed over 8, which means that r is equal to r over 2, which is c. Okay. Asteroid has that mass and that escape velocity. This is gravitational. This is a gravitational potential. Yeah. Order of magnitude of the radius of the asteroid. Escape velocity. That's when gmm over r from the distance equals the kinetic energy half mv squared. Or actually that mass cancels. We know the velocity. Okay. We know it has that mass. What's the order of magnitude of the radius? Huh. Escape velocity. That is certainly when gmm over r is the gp, has to equal that. It's an asteroid. Escape velocity from what? Oh, escape velocity from the asteroid. Got it. Apologies. That was me Okay. Okay, so we know G, we know M, we know V, we can get R. This is fine. So 2gm over V squared equals R. G is equal to 6.67 times 10 to the minus 11, I believe. Perfect. So 6.67 times 10 to the minus 11. It has a mass of 2 times 10 to the 17. That is meant to be a 2. All over 40 squared. So 2 times 6.67 10 to the minus 11 times 2 10 to the 17 all over 40 squared is this many meters. So that's 10 to the 4 meters. Okay. Yeah, the multiple choice. This is not fun, guys. All right. Gravitational field for a binary star. Equipotential lines are shown. Gravitational field lines are shown. More work is done moving from Q to S to R than moving directly. That is not correct. Exactly the same amount of work is done there because you just move along the equipotential. So there's no work done moving from S to R. So they're the same. No work is done moving from Q to R. Wrong. You're changing equipotential lines. Work is done. Gravitational field strength is the same at R and S. I'll come back to that. Work done moving from Q to R and moving from Q to S is the same. That is definitely true because you're moving between the same equipotential lines. Gravitational field strength does not need to be the same because that's the negative of the potential gradient. And it's to do with the proximity of the field lines there. So actually at R, we can see the field lines are somewhat closer together than they are at S. There's a bit of separation there. So that's the one I was less certain on. So as this is the case, sometimes where you're like, I don't really know what you're getting at, but you kind of just like wait for something to give you a bit more certainty. Done. No, not relative permittivity. Haha, no. Relative permittivity of a vacuum is 1. Ooh, nearly fell for that. Nearly fell for that. So we know that C equals epsilon naught A over D. Which is Q over V. C equals Q over V. Q equals CV, yes. So it's the charge stored on a capacitor consisting of 2 parallel plates when A is 1, D is 1, and thing is 1. That looks good to me. Why is it not the others? Relative permittivity of a vacuum is 1 because that's epsilon R, not epsilon naught. The work done when moving 2 coulombs of charge from infinity to a distance well, okay, the work done, this work done would be equal to 1 over 4 pi epsilon naught Q 1 Q2 over R. No, so if you're moving at a distance of pi, you would have your, that wouldn't cancel out the pi. So that's why it's not C. The charge on a metal sphere which experiences a total force of 1 Newton when it's centered. So force is 1 over 4 pi epsilon naught Q1 Q2 over R squared. And again, nothing is canceling that pi. So that's why it's not those. Cool. The force between 2 point charges is F. The magnitude of each charge is doubled and the distance is halved. So the force is, I'm going to call it K, Q1, Q2 over R squared. The magnitude of each is doubled. So that gives a multiple, that's 4 on the top. And the distance between them is halved. So that's a quarter, so it's 16 times bigger. So that's A. So sometimes if you're confident, you can just use your proportionality. If you're not confident, I advocate for what I call a before and after technique, which I kind of alluded to before. So I would get, if you want a rigid method, I like to get everything on one line and then write it out twice, once for the before case, once for the after case. So F2, R2 are these things. So what we're told is R2 is a half of R1. And that is twice times the first Q1. and that is twice times the first Q2. So a quarter F2 R1 squared equals 4K Q1 Q2. But we also know from rewriting this, we know that F1 R1 squared is K times these relative charges, right? So F1 R1 squared is K Q1 over Q2. Now, if we divide those through, the benefit of this method is just like everything cancels. So a quarter F2 over F1 is equal to 4. In other words, F2 over F1 is equal to 16. And F2 is equal to 16 F1. So some people who really don't like to handle proportionality, I find this technique can kind of help them get through unscathed. Where again, you get everything on one line, write it out for the two cases, divide through, everything cancels. Okay, so distribution of charge where the electric potential at P and the electric field at P are both 0. Well, let's start with field. So in this case, the field at P is not 0 because positive charge will want to move downwards. Here, a positive charge would be balanced out because it's being squeezed, it's being pulled in both directions evenly and pushed in both directions. Here evenly, here. No, a positive charge will want to move towards the bottom right, so it's not C. Here, a positive charge will be attracted both that. Yeah, so this looks good from electric field. Now, electric potential is the work done bringing it from infinity to that point. D. Spoilers. Let me think about this. So from infinity to that point, yeah, the positive charge has to do more work against the repulsion of these guys than it gains back from the attraction of the negative charges. So it's correct that this will not have an electric potential of 0. But here, the work done in being attracted by the being repelled, the work done against the repulsion of these 4 Qs to get to this point would be balanced out by the attraction of these 4 Qs to get to that point. So the potential would be 0 there. Or you could argue, like a commenter just did, that the sum of all the charges is 0. That is a nice workaround. Boop. All right, 27. Ion a specific charge of that. Held stationary in a vertical electric field. So what that means is an ion is a negative charge. It's held stationary because it counteracts the weight, where F equals EQ. So we know that this thing experiences an upward force when it's negative. So in other words, this would be achieved by positive plate, negative plate. So we know the electric field points downwards. And we know that EQ equals mg. Specific charge is Q over M, which is equal to G over E. In other words, E is equal to the G, which is 9.81, all over the specific charge of 7.1 times 10 to the 7. So it'll be way less than 1, so it's B. And that's how to argue that. Granted, I could also run the numbers, but that's why that works. Exactly as the commenter has said. So which particle pair has the largest magnitude of electrostatic to gravitational when separated by the same distance? So that would be KQ1Q2 over r squared divided by the gravitational force of G m over r squared separated by the same distance. These will cancel. So in other words, it is just K over G times the specific, no, K times the specific charge. I don't know what the symbol for that is. I'm going to call it bar. So the specific charges of both. So in other words, it's proportional to the product of the specific charges. Electrons, helium, absolutely not. Too many neutrons, bad. I'm going to say positive pion only because I know nothing about particle physics, but I think a pion is less heavy than a proton. So yeah, I'm going to go for A. What can be deduced about the radius of a nucleus from the scattering of alpha particles? The radius of the nucleus is about 10 to the minus 15. Although I'm not sure. Hold on. Can you conclude that from the experiment? I know that is true, but can you conclude it from the experiment? So this is the classic one where very few of the particles are deflected by more than 90 degrees, which means that the nucleus is very small and in the center of the atom where it contains almost all of the mass and charge. I think, yeah, I'm just going to go for C because it is true. Yeah, I'm going to go for that. I could be wrong about that. I might be missing some niche knowledge point there. So this guy, 115.45. And so 115.45, damn. All right, you want to lose. No, lies. N is the neutron number. So the neutron number here is 115 minus 45, which is 70. So 70.45 is kind of there. And you are radioactive. You make yourself onto the stability belt by losing neutrons and gaining protons. And the way you do that is through beta minus decay to turn a neutron into a proton. Okay. Uranium-238 absorbs a neutron in the first stage of nuclear reactions that ends in a nuclide Z. How many neutrons does it have? All right, so it gains a neutron. So that's 23992. That does absolutely nothing. This is 239. That makes it gain to 93. And then it's going to be 23994 for another beta minus. And then 239 minus 94 is 145, which is B. Okay. Did not contain any lead. Uranium-235 decays by a series of steps. Half-life is that. Negligible. So this now contains 1 atom of lead for every 4 atoms of that. So what that means is it was so if we can consider the uranium to lead, it was 5 to 0 and it's now 4 to 1. The reason why I say that is every single one of these leads has to have come from a uranium. In other words, 20% of the uranium has decayed. Now we know that N equals N naught e to the minus lambda T. we know that lambda is equal to ln2 over the half-life times 10 to the 9, and we'll do this in years. Or rather, hold on a minute, what we can say instead, let me do that later. What we know is that n over n naught for the remaining uranium nuclei is 0.8. So 0.8 is e to the minus lambda t, which means that lambda t is equal to the negative of the ln of 0.8, which is 0.223. Now lambda is ln2 over the half-life. So the age is the 0.223 times the 0.71 billion years all over ln2. This feels like I've done something wrong, but let's find out. It gives me 0.22. So, oh no, it didn't. 0.23. That is end of questions, but I did skip a couple. So let me go back, because the second you think you're done with the paper, always check to make sure you've answered every part of every question. I skipped this because I just didn't like the way it was phrased. Let's see if I can do this now. So the gas expands. All right, here's why I don't like it. It's because in my head, I'm like, oh, well, it does 1660 joules of work, which means it now has, 3340 joules left. But if you do PV, the pressure is the same and the volumes increase, so the left-hand side should increase. So no, but the final temperature should go down. I would expect the temperature to go down. No, is that true? No, same pressure. Volume goes up. So the left-hand side is bigger, so the right-hand side has to be bigger, surely. Why is my brain just blah? Okay. Also, help the chat if I'm missing something and you want to spread it. Feel free to put it in. But I can see why this one would trip people up just from how it's worded. But if you expand, oh no, if the temperature goes up, the volume goes up. Why don't we do that? Why don't we say it goes to 6660 equals this thing. So this thing is 5,000 over 300 times the new temperature. And so I'm going to suggest that the new temperature, I'm not confident on this, over 5,000, but this is like how I'm piecing it together. 6660 times 300. But also, look how much I've not put pressure on this question by doing it right at the end. Oh, no, yeah, so I'm getting 400 Kelvin from that. Cool. And this one, I didn't like the way it was worded. Decreasing the frequency versus decreasing the diameter of the copper wire. I think... I think it's decreasing the frequency. I think, okay, what I just did was I went to the syllabus. All right, what are some of the things that cause power losses in transformers? One of the things that came to mind was hysteresis loss. This is due to changing the magnetic field back and forth. It's not perfect, and some energy is required to flip that. If you are decreasing the frequency of the AC input voltage, you decrease the number of times you have to flip the magnetic field back and forth. So you will decrease the hysteresis losses, and that will increase the efficiency of the transformer. I was hesitant about C anyway. Well, no, if the diameter is decreased, that would increase the resistance of the copper wire anyway. Yes, you're quite right about that. And I don't know why I overlooked that the first time. Clearly brain fart, but again, you come back to it with fresh eyes, and that's how it works. But I think that's what they were going for. Now, let's find out, because again, my brain is so not at 100%, so I don't expect to get 100%. but let's just see how I did. And if I get one wrong, I'll then at least be able to explain it so you understand it, right? Even my mistakes are going to be instructive here. And you can watch me go through the process. How do I get myself out of a bind? Exam technique, all the good stuff. So let's have a look and see. Well, in fact, what I'm going to do is it's going to be faster if I just have the mark scheme over here instead, actually. Oh no, what am I doing? I'll just stop that. I don't know what just happened. I did not mean to link these. Let's put you over here. And let's put you over here so we can see you side by side. I'm going to scroll down to the multiple choice section. Okay. And if I share the entire screen, you can see both at the same time. Cool. So 8 is B, 9 is C, 10 is B. I did get that right. I was not confident, but it was how to do it. 11 is B, 12 is B, 13 is C, 14 is D, 15 is A, 16 is D, 17 is C, 18 is A. Oh, they do explain it-ish. 19 is A. It wasn't a trick question. I did get that number, but I doubted myself because of that was really tricky. That question really got in my head. I shouldn't have overcomplicated it. I should have just demonstrated my exams technique there, or like my syllabus knowledge there. Okay, interesting. So here 20 was D, 21 C, 22B, 23D, 24B, 25A, 26D, 27B, 28A, 29A. Yeah, I wasn't super confident on that either. Oh, of course. All right, let me explain why that's the case. First of all, let's see what they say. Oh, that's just the answer. Okay, here's why, guys. We know the actual radius of a nucleus is about 10 to the minus 15. What's coming to mind now that I neglected was the idea of measuring the radius of a nucleus from the distance of closest approach. And remember that the alpha does not make it actually to the surface of the gold nucleus. So actually, you would be if that's where it stops, you would be measuring the true radius as being a bit bigger. So if the closest approach is about 10 to the minus 14, we know the actual nucleus is somewhere under that, which that's why I think the answer is A, because of the distance of closest approach of the alpha not making it to the actual nucleus. So if that's going to be why, that's going to be why. So I missed that as a knowledge point. Sneaky question is sneaky. 30 is C, 31 is B, 32 is A. End of questions. Okay. So that'll be why that happened. So a couple wrong there, not too bad. Those were both like legitimate, okay, fine, you tricked me, you win. That's very niche knowledge, I think. And again, this is one of those. The other one, the energy one, is a classic get in your head question. Where there were two legitimate things, and I was thinking like, is that energy being released from mass loss, or does that count as like just chemical bond? Yeah. Sneaky. 19 is confused. It would be, I mean, it could be easy because we know the mass loss is definitely in terms of the binding energy and all that kind of stuff when it comes to nuclear reactions. I don't think we're as used to it when it comes to these chemical reactions. Because none of the elements are changing. They're just rearranging. And so I wouldn't expect the masses to really change all that much because it's the same number of carbons, hydrogens, and oxygens before and after. So it's not like you're getting any nuclear stuff. So that one, I don't feel bad about getting trapped out by that. But right, because I got half an hour left before my next session. So I can go on to, I won't have time to do both. Chat, do you want OCR or do you want Edexcel? Wouldn't the mass be lost when burning? If by mass loss you mean the fact that it's turning into carbon dioxide and so being lost, then sure. Right, someone's coming with OCR. Earlyworm gets the bird. Let's do it. That's the mark scheme. No, why did I do that? Okay, so that's the paper. That's the mark scheme. Okay. Let's full screen this. Let's see how much of this I can get through. I'll stop with enough time to mark it. Oh, about 30 minutes on the section. That's great. I've got 30 minutes. Base units of a kilowatt hour. That's joules. The end. Neutrinos of, don't make me do particles. It's a lepton. Certainly not a hadron. Which means it feels weak nuclear, which is D. I hate them. Non-invasive medical scans does not expose the patient to ionizing radiation. That would be ultrasound. 3 capacitors arranged in the circuit. What's the total capacitance? Well, these are in series, so I'm going to add them the way I would have done. Now, this is something that's not on the Edexcel syllabus, but combining capacitance, this would be done the same way as resistors in parallel. So 1 over C would be 1 over 0.33 and 1 over 0.22. So if I run that on the calculator, 0.33 to the minus 1, 0.22 to the minus 1, all to the minus 1 is capacitance here would become 0.132. And then you add these together. So capacitors in parallel add together, and the total is 0.60, which is B. Micrometer, okay, so that's 0.51, 0.52, 0.5. So that is, I was gonna get that. Never mind. What's the point in showing you if they're just gonna tell you? Because it has an error. Oh, it has a 0 error. So it's 0 error is plus that. So the true. So if on 0 it's measuring that, I think the true would be 2.81. That's going to be the test here, is whether you add or subtract that. So the correct cross-sectional area is pi, and that's going to be d squared over 4. So it's pi times 2.81 times 10 to the minus 3 all squared all over 4. When I run that in my calculator, I get 6.20 times 10 to the minus 6, which is B. And I hope I did not get 0 error the wrong way around. Display evidence, because you'll find that my understanding is flawless, but my knowledge is not always the best. Right, so, and so if this like knowledge point of, God damn it, what does that mean? How much exact, or like particle stuff, I'm like, boo. Which is measuring an alternating voltage. Time base is set at that. Voltage is that. Amplitude and frequency. That's 0.4 seconds, which means the frequency is 1 over that, which is 5 over 2. But let me just confirm it, because brain, not braining. 2.5 hertz. Amplitude is from these guys, so it's 1, 2, 3.5. And 3.5 times 0.5 is 1.75, so that's B. Rate of decay of radioactive source. The rate of decay is, depending on the decay constant, I think that's true. Well, because the The rate of decay is the activity, which is a naught e to the minus lambda t. So yes, independent of the mass of the source. It's not independent because activity is equal to lambda n. So in other words, it does depend on the number of nuclei that are there, and therefore the mass. I suppose it depends on if the mass is entirely thingy, but I wouldn't say it's independent. And the rate of decay is dependent on time because it decreases over time. So 1 and 3, so B, although I could end up being a little wobbly on some of the technicality there. One of the decay of a charge on a capacitor, they're using that equation. Time interval of 0.5. The charge of the capacitor is that. Okay, so in other words, that. So what they did was they did 600 over 2.5 to get the 240. And that is what they said. Okay, so that 240, so 600 over 2.5 is 240. What they said is that is dq dt, and therefore over half a second, they multiplied by that half to get that 120. They then subtracted that 120 from the 600. Let's keep repeating this process. 480 divided by 2.5 is 192. And 192 would be for a full second. So for a half second, it would be 96. And 480 minus the 96 is 384. 384 divided by 2.5 is 153.6. Times 0.5 is 76.8. 384 minus 76.8 is 307.2, which is D. And don't be tempted to fill out the whole thing, by the way, because it wanted specifically T equals 1.5. Oh God, I love stationary waves. Is this definitely the right? Is this paper 2? I'm sure it's paper 2. Let me check I'm getting this right. Yeah, it's 2. Okay, we're fine. Yeah, I was gonna say, like, this is not the way that AQA works. I was like, wait, what? I don't, yeah, I'm like surprised, but hey, I selected a paper 2. Are the paper 2 topics just okay? Clearly very, very different topics, but that is decidedly paper 2. I'm as shocked as you are. Okay. But look how long it took me to be like, wait, what? It was like, wait, waves shouldn't be showing up. So what's the phase difference between P and Q? This would be, they would be 0. Because in standing waves, it's completely out of phase when you're on the side of a node, and then flipping back would be completely in phase again. EMF and internal resistance. So clearly, like, this is all just flipped. EMF is the y-intercept. Internal resistance is the magnitude of the gradient. Yeah, it's D. Oh, here we go. So yeah, apparently it is just a mix of everything. So the Earth's equator magnetic flux density is that. What's the magnitude of the force on an electron with that? So BQV equals mv squared over r. The force on an electron is just BQV, actually. So 25 times 10 to the minus 6. Electron, 1.6 times 10 to the minus 19. V times 100 kilometers per second. And then just running the numbers, we get 4 times 10 to the minus 19, which is C. Okay, so going back to the formula sheet again, I'm not going to get the specific one for this exam board because time. And at a certain point, equations are equations. But r equals r naught a to the third. So it's going to be 1.2 times the cube root of a is that's at 13. So 1.2 times the cube root of cube root of 13 is 2.8 femtometers is C. Subatomic particle has a positive charge. What? No. I wouldn't call a positron subatomic. Antiproton is negative. Up, down, strange charm, top, bottom. So here, down quark has a charge, is negative charge, which I should have known actually. Up is positive 2/3. So it's a positron. So yeah, I mean, a positron's not in an atom, but I suppose, yeah, subatomic particle, I'll go with it. So here, what's the reading on the ammeter? Oh, these are cells. Oh my God, I thought they were capacitors for a second. I was like, what's going on? So negligible internal resistance means we don't need to worry about this. So these are just in parallel. This is still just 1.2. So total is 2.4 volts. So I equals V over R. So I will say these are easier in difficulty as compared to the AQA ones I'm seeing, which is good. Show the energies below an increasing order of magnitude. Change in kinetic of through potential difference of 1. So we know that voltage is work done per unit charge. So work done is equal to voltage times charge. So that would basically be 1 electron volt, which is 1.6 times 10 to the minus 19. Kinetic energy of a proton. So a half times, well, it's certainly bigger than 1. So 2 has to come after 1. So it's not 3. Energy of an X-ray photon with that frequency, E equals HF. H, cannot remember off the top of my head. 6 points, no. I should know this. It's just been a while since I've used it. Yeah, 6.63 times 10 to the minus 34 times 3 10 17. 10 to the minus 34 times 3 10 17 is 1.99 times 10 to the minus 16. And just for security, I will calculate. So this the kinetic energy would have been a half 1.667 times 10 to the mass of a proton. Oh, got that wrong. 1.67 times 10 to the minus 27. Added an extra 6. Boop. 10 to the minus 27, half mv squared. 0.5 times 1.67, 10 minus 27 times 1,000 squared is 8. Yeah, it's huge. No, it's tiny. 8.35 times 10 to the minus 22. I was dead wrong. Was I dead wrong? Huh. Okay, so it looks like it's 213. So it is C. It's the only one I discounted. All right. See, this is why you go through it. And that seems to be it. That seems to be the multiple choice. Let me mark up. Come on, whoop. Is that mark scheme? Hold on a minute. Okay. Just getting everything formatted nicely. So, 1C. Oh, are you kidding? Oh, I'm an idiot. I'm an idiot. Guys, I'm an idiot. I got complacent. You see, that's when it happens. Complacency is when you start making mistakes. Is a kilowatt hour base joule? Yes. Is joule base unit? No. God damn it. No. No. I was so overconfident. No. Okay. Sorry, guys. I'm going to blame the lack of sleep. Oops. Joules, as we know, so the way to think of that is a joule is force times the distance. F equals ma, so it's kilograms times the acceleration, meters per second squared, times the distance of meters, so it should have been C. Nailed it. Absolutely crushed it. Right, 2D, 3C, 4B, 5B. I got that the right way around. 6B. I didn't write it in, but it's B. 7B, 8D, 9A, 10D, 11C, 12C, 13D, 14C, 15C. Yeah, all good. Okay, I think there's probably not enough time left to do the Edexcel one, just because there's only 15 minutes left. Happy to stick around and chat, though, if anyone's got any questions ahead of the paper 2, which I think is tomorrow. How you guys feeling about it? The crowd goes wild. I like tutoring normally from the sort of interaction. We would kind of normally get a bit more of a dynamic, lively chat, but you know, you guys are silent to have to take time to type. But hey, that's the way it is. Hopefully you guys took from that, like the exam technique, looked, you know, sort of looking at how I moved through it, looked at the mistakes I made, why I made them, especially those tricky ones where you're like, oh, it could be that or it could be that, and they both seem viable, like how you kind of get around that. The AQA was difficult, so it shows you how much they want you to really know those knowledge points, the differentials in, like, I say differentials as if it's math. What I mean by that is like the little differentiating knowledge points in all the little nooks and crannies of the syllabus. So maybe spend some time today just like, but the problem is you have no idea which nook and cranny to look into. And if this is the day before, then like, maybe not like stressing out about every little thing, but look at this sort of exam technique of how I like eliminated possibilities. Then if you're guessing between fewer options. Look how I went, ew, I don't like that question. So I didn't fret over it. I just skipped it and came back to it with fresh eyes. That's really good. What's the best way to approach thermal calculation questions for AQA? I would say set up the word equation first. Energy lost by water equals energy gained by ice, and then fill everything in. But once you have that structure in place by setting up the word equation, then you should be in a much better place to calculate it correctly. Oh, that will still be useful for it's never too early to learn exam technique. Exam technique is life. Because a lot of people get really stressed if they can't do a question, because what they're thinking is, what does this mean? But they're not trying to solve the paper at that point. They're trying to like work on their own psychology. So the answer is nothing. It means you're tired. It means it's not a good question. It means it can come at the end. It means nothing. That's why I advocate for a multiple pass strategy in any multiple choice, because then you're doing the questions early that give you the confidence and momentum. So it kind of settles you into the paper, calms your nerves, and doesn't have you thinking, what does this mean? Oh, is this a bad paper? Oh, or do I not know as much as I think I do, right? You just sort of go, next, get all the good ones. And then look, by the time I came back to it, I was like, out of 40 questions, I'd only skipped 2. They came quite early on, but I only skipped 2. And so I was like, oh, it's just 2 questions. Instead of thinking, oh, this is the second question and I'm already stuck. Like, there's a good way and a bad way to handle that psychologically. So head in the game is what I would say. You have a duty to all the questions, not just the one right in front of you. I would say as well, let's have a look at what's coming up for you guys this week, because I know you've got your Phys 2 tomorrow. Some of you guys doing CIE have stuff this week. I know I've got a student doing that. Your Math 1 is on Wednesday. I should have a live solve coming out tomorrow. Yes. It's fine. Should have a live solve coming out tomorrow. I think I'm going to carry on with the OCR MEI paper 3s just because they're weird and fun. Ooh, common question. Apologies for ignoring you. Why is gravitational potential a scalar quantity? Because it's energy. Potential is energy per unit mass. Both of those are scalar quantities. Gravitational field strength is force per unit mass, which makes it a vector. So just think about the underlying definitions. Now remember that fields are all about field strength, which is pertaining to force, or potential, which pertains to energy. Gravitational affects mass. Charge is what is affected by electric fields. So if you just remember those core definitions, you should be fine. By the way, when it comes to the math, remember, whenever you think you're done with the question, reread the question to make sure you've actually got over the finish line. Whenever you think you're done with a paper, in any paper ever, check to make sure you've answered every part of every question. Check to make sure you haven't skipped a question and then forgotten that you skipped it, and then you like forget to come back to it, and then you're checking your work and then you realize too late you missed it. Just make sure there are answers to all of the questions first, then you begin your checking process. Maybe as you go, you can make a note of the questions that you didn't feel as confident on to give them a sort of look over with fresh eyes, even if there is an answer there. There's so many things you can do to just maximize your chances of not making execution errors, not making exam technique errors, and getting every mark you deserve. So we done did an A-level physics. Congratulations, guys. Well, I say that. Sorry, I forget there's a paper 3. Oops, my bad. So what I'll do, this week is looking quite busy, but I think the weekends are where I'm going to keep, that's where things are a little less busy for me. It's where I think I'm going to do my streaming. I should have a live solve out tomorrow. I'm going to see you guys at some point in the weekend, be it Friday or Saturday, not next Sunday. So it'll be Friday or Saturday. We can go through more of the paper 3 techniques. Maybe I can do a live solve of a paper 3. Paper 3 is just so ugly. Physics paper 2 debrief. Oh, I would love to do one tomorrow, but I am so not free. The only possibility I have for that is on Wednesday, which would also be after your math paper 1. So maybe we'll do that. Maybe we'll do a physics paper 2 / math paper 1 debrief Wednesday evening at like 4 p.m. Thank you for that. That's a good suggestion. That'll be good fun. And I do have that slot open. So that sounds good. In fact, let me put that in now while I remember. Because calendar is life. Phys 2 math 1 debrief. Okay. So I'll put that in to remind myself. Thank you for that. And in the meantime, keep working hard. I'll see you guys when I see you. All right. Take care. Good luck with the physics tomorrow. Bye-bye.